This is our tutorial on factorial ANOVAs. With a factorial ANOVA, we're looking at more than one independent variable being tested across one dependent variable. We're looking for differences among different groups and also some other characteristics. So we're going to be dealing with more than two groups, and we're going to be dealing with more than one independent variable. For example, I could look at first-year students and second-year students and compare those students who are full-time and part-time. So I'm now looking at the interaction of these independent variables, not just each independent variable independently. And that's where the power of the factorial ANOVA comes in, because I can look at the interaction. We'll talk more about that in a second. So we have two types of factorial ANOVAs. We have one without replication and one with replication. The with replication is also known as repeated measures. So with replication or repeated measures, we're testing the same individuals more than once across time, whereas without replication, we're testing two different groups. So you can liken the without replication to the independent t-test that we did previously, and the repeated measures is much like the dependent t-test that we did before, except now we're looking at more than two groups. So here's an example. We have a treatment and we have a severity of illness. The severity illness is broken across severe and mild. In the treatment, we have three different types of treatment: drug 1, drug 2, and placebo. Now, here I've given you a template to help you draft up research questions for factorial ANOVAs and also the null and alternative hypotheses. Let's see what that would look like with this particular example with the severity of illness and treatment. So, is there a difference between the effects of symptomology between three drug treatments? So, drug 1, drug 2, and a placebo. You see, there's no severity of illness in this particular question. This is called a main effect. We're just looking at the treatment. So, we're looking at the within group differences. Are there differences between drug 1, drug 2, and the placebo? So, that's a within group difference. Is there a difference between the effects of symptomology between severity of illness, severe and mild? Another main effect, the second main effect. And there again, we're looking within the group. Is there a difference? We also can look at the interaction. Is there an effect of the drug treatment different from severity of illness for severity of illness? So this is looking at the type of treatment and the severity of illness. If the interaction of those two things causes significant differences or has a significant difference. So this is the power of factorial ANOVA. We can look at main effect, a main effect for each independent variable, and we can look at the interaction effect for the two variables together. This is explained here. For degrees of freedom in our factorial ANOVA, it's much like the other ANOVA that we've looked at, in that K represents the number of observations. So in this particular example here, we have 6 observations. We have 6 groups, right? We have the severe drug 1, the severe drug 2, the severe placebo, the mild drug 1, the mild drug 2, and the mild placebo. So there's literally 6 groups of people that cannot be in more than one group that we're comparing. These are also called observations. So for our numerator, K is the number of observations minus 1, whereas the denominator of our degree of freedom, or second number in our degree of freedom, is N, the sample size, minus the number of observations. So why do we not do t-tests? Well, one, we'll have to increase our risk, as we saw in the ANOVA tutorial, that we would have to multiply our risk by, or we'd have to raise our risk to the number of observations. Also, we would never know the interaction between the independent variables, which is a powerful component of factorial ANOVA. Same assumptions as before. We just now have 2 or more independent variables that are categorical or nominal, 1 dependent variable that's continuous. Groups have to be independent of each other and ideally of similar sizes. Our dependent variables should be normally distributed, and we can use a QQ plot to see that. We also want to see no significant outliers. And we want homogeneity of variance, a similar spread between our groups, or our F statistic may not be reliable. So we're going to use our Levene's test of equality to test for that. We're hoping for a non-significant result there to show normality. So we're going to take a look at weight loss as our data set. We're going to look at two genders in this particular study, male and female, knowing there's definitely more, but this is male and female in the study. And we're going to look at the impact of a weight loss or exercise program. So we have a low impact exercise program and a high impact. And the dependent variable is going to be weight loss. So again, you can see that here. Our independent variable 1 or factor 1 will be gender. Independent variable 2 or factor 2 will be treatment, and our DV is our outcome is weight loss. We're going to say there are no differences between high and low impact exercise. We're also going to say there's no difference for gender, male and female, by weight loss. We're going to look at our interaction effect, which is going to say there's no difference between male and high impact, female and high impact, low impact male, or low impact female. And then we'll do the same for our research questions. We're going to set our level of risk at 0.05, as we normally do in social science. We will not have to calculate the critical analysis because we'll be our critical value, because we will be running this in JASP, and it's going to tell us what our exact p-value or significance level is. The appropriate test is a factorial ANOVA because we have two independent variables, treatment and gender, and one dependent variable, weight loss. We're going to compute this statistic in JASP. So let's open up our weight loss data file. We will need to do some clarifications on our data for treatment. 1 is going to be high impact, 2 low impact, and gender is going to be 1 male and 2 female. So let's take a look at that. Move this over here. Okay, so this is my data set. All right, so I have treatment, gender, and loss. Treatment and gender are both listed as nominal, so yay, that's good. And loss is listed as a scaled variable. I want to clarify this, so when I break out my charts, I'll know what this means. So as I mentioned, I'm going to click here, treatment. So my first label is going to be high, and my second label is going to be low. This is standing for the type of exercise. Okay, so I fixed both those. And then gender, I'm going to click here. The first one is going to be male, and hit enter. And then I'm going to fix 2 to female, enter. So now my data set is more clear and I understand what I'm looking at. I'm going to go to ANOVA, classic ANOVA. And this time I have 2 fixed variables. So I'm going to move treatment to fixed variable factor, and I'm going to use gender to fixed factor. I'm going to move loss to dependent variable. I'm going to go ahead and click descriptive statistics, estimate my effect size, my model, my assumption checks here. I'm going to click homogeneity, Q plots. I'm going to hold off on post hoc for a second. For descriptive plots, I can look at these individually, but I also can look at them together. So if you look here, it's going to give me just the treatment, or I can move this back and I can move gender, and I can get a chart for gender. But it's probably more helpful to see the 2 together. So I'm going to put treatment first. Calculated, there it is. So this is my treatment. And now I'm going to also put on separate fact lines, I'm going to put the gender. So now you can see, here's my high impact. I have my male here and my female here. For my low impact, I have my female here and my male here. So it's kind of helpful. I can see both of them in the same place. I'm going to display error bars too. It's going to make this graph a little more complicated, but you can see this is my confidence interval of how confident I am that this is the accurate representation of the population. If that's too much, you can take that off. I'm also going to look at, I'm going to hold off on marginal means actually. So let's look at our results first. All right, so I'm going to go all the way to the top to my source table. This is the source table, and I'm going to look at my first main effect treatment. I'm going to go across, and I'm going to go to P here to determine if it's significant. In this case, it exceeds 0.05, so it is not significant. So treatment did not demonstrate significant differences between high and low. I'm going to look at gender next. In gender, it's 0.1757. Again, this exceeds 0.5, so I'm not seeing any significant difference between male and female. However, when I go to my interaction, I am seeing a significant finding. So isn't it interesting? The main effect was not significant. Main effect 2 was not significant, but when I account for both those and I compare the 4 different ways that can look, high male to low female and whatever, or the 6 different ways that that can look, then I'm going to, it's actually like 4 ways that that will look. I can see that that interaction is going to be significant. So what that means is when I do my post hoc, I don't need to run it for treatment or gender. In fact, I don't run it for treatment and gender. Same thing's true for my effect size. Remember, I'm only going to, let me clear this up. I'm only going to interpret this effect size. This effect size and this effect size are not meaningful because you have to have a significant finding to have a meaningful finding. Because I have a significant finding here, I can interpret this effect size. So we will do that in just a minute. I'm going to go on down to my post hoc. And for my post hoc, here they are, post hoc, I'm only going to move the interaction effect over. Okay, and I'll go and I like Bonferroni and Tukey. So I'm only interpreting that post hoc. I can't interpret these because they aren't significant. So they wouldn't mean anything even if I ran them. So I'm going to scroll down. Here's my post hoc. This gives me my post hoc comparisons or pairwise comparisons. So my high impact male to my low impact male is not significant. You can see that here in both types of post hoc. Same thing for high male to high female, no significant difference. High male to low female, no significant difference. Low impact male to high impact female, no significant difference. Low impact male to low impact female, it is significant. This is less than 0.05. So I would interpret this one and this one as being significant differences. So now I not only know where my differences are, or what my difference is, this is what's the difference, right? Like there is a difference. And then down here, it tells me where that difference is. Okay, so now let's take a look at it in the notes. Here's a note page. So this goes through all the steps that we just took. And we see that we went through our assumptions. We met each of the assumptions and how we met those assumptions. There was one potential outlier here. So we would have to make a decision about whether we would keep it or throw it out. That is truly just a decision you have to make. It's not one that can be made for you, and you have to have your rationale for it. If I wanted my groups to be equal, then I probably would keep that one, right? Because when I look at my data set, I think I had an even split. This is by gender, it had 40, but it doesn't say which one's male or female. But I'm pretty sure I had an even split. So I'd probably keep it just because it would keep my groups equal. This talks about my equality check, which was again not significant. So that means that there was normality. Here's how that all is interpreted. Here's how I would interpret my results. Here are my sentence decisions for each one. The interaction, I would report all 3 of these, and this is what that would look like. Is it meaningful? Remembering I'm only interpreting gender, treatment versus gender, or the interaction. It is a large effect size because it's greater than 0.14. Here's that interpretation. And remember, I'm only interpreting for that one. Then I'm going to look at my post hoc for the interaction. And again, these are, let me go ahead and insert that shape here. These are the only 2 that are significant. So no fill. So here we go. So these are the only two that I'm going to interpret because these are the only two pairwise comparisons that are in fact significant. Here's how I'd interpret the post hoc. It's also helpful to look at your marginal means. With marginal means, I'm seeing each of the treatment with the gender, and I'm seeing what the marginal mean is with the confidence interval here. And this is how I would interpret that confidence interval. It's saying that I'm 95% sure that the low impact male participants lost an average of 78.8 pounds, and I'm 95% confident that the true weight loss of the low exercise impact male participants was between 72.1 and 85.5. I can also use error bars, like we said before. I put those in here, and that shows you the interaction between those. This is all of what I've done in one full description. So a factorial ANOVA was conducted to determine whether the type of exercise impact, treatment, and gender have an impact on weight loss. I go through to describe my assumptions, and then I talk about the difference in my source table. And then I go and talk about the differences in my post hoc and describe those differences. Okay. And I'm looking to see if, oh, interesting. I will fix this in the book, but I don't see where I included this part. So I would copy this. And I will add this to here. I don't know why this isn't in here. So you should interpret this first, and I should interpret the effect size first. So those two pieces appear to be missing. So I'm going to add those here. Okay. So now I have a full description. Now, I have a bonus question for you. Why is it only appropriate to do a post hoc analysis if the F ratio is significant? Remember from our previous discussions about this, you have to have significance to have meaningfulness. If it's not significant, it's trash. You don't need it. It doesn't show anything. So there wouldn't be any need to interpret the meaningfulness, and there definitely wouldn't be any need to look at post hoc comparisons, because if there's no significant difference, then there's no difference to explore. I hope this has been helpful. Please let me know if you have any questions.